Hello guys. So, Today we'll be solving the Leetcode question, finding the duplicate number. So, in this, we are given an array nums, which is containing n plus 1 integers, and each integer is in the range 1 to n. So, this is our input nums array, and we want to give out a duplicate element. Okay. So, there are certain things inside this, like if the array is having n plus 1 integers, so 1, 2, 3, 4, and there has to be one duplicate element. It could be either 2, 1, 3, or 4, something like this. So there are 5 elements, and you can see that the range of these elements are within 1 to 4, right? So this itself is a proof of why why a duplicate element will exist. Because on one hand, you are saying that only 1 to 4 numbers would exist, right? And there will be no repeating elements. So the maximum that you can have is 1, 2, 3, 4. But now, if you want plus one element, because these are the n elements, and then you are saying that your array is having n plus 1 integers. So that means definitely this place at least one of the four numbers will be there, right? So saying the statement that it is containing n plus 1 integers and having a range of 1 to n itself says that there will at least be one duplicate number inside your array. Okay. Now, how do we solve this problem? One constraint that they have given is without modifying the array. Okay. So we have two approaches basically. The only thing is this is not a very easy kind of a problem, or the intuition of this is not very straightforward. Even I took a lot of time myself to understand this, and I was not able to do it myself. So there are there is one approach which is there using the tortoise and the hare approach, and second approach is where I will tell you if this constraint is not there. If you could anyhow modify the nums array, then you can definitely do using this approach, and it is not that complicated like the first approach. The first approach is definitely complicated. So I will be explaining you the first approach first, and I will be going through all the proofs. You will not be needing to try out or separately see other proofs on the internet or anywhere else. So I will be going through each and every detail in this video itself, and then I will be also showing the second proof. Okay, so before we start that, let's just see how a normal person would be trying to achieve this problem. So this is an example one. So here we have 1, 3, 4, 2, 2, and the output definitely 2 is the repeating element. How can you do this? If you want to see that there is a duplicate element, you have to store it, right? You have to store. You store 1, then you store 3, then you store 4, then you store 2, right? And when you come at this 2, you will check in the map that, okay, the element is already existing. So at that point, you can stop. So this will take kind of order of n log n, right? Why n log n? Because you will be storing these elements, and you will be also searching in this hash map, right? So this is the hash map if it is in Java, or a map in or an unordered map in C++, right? So it takes log n to find, right? And you will be iterating through all the elements, inserting and searching that. Those are the log n operations. So this will take time, right? Order of n log n. And what is the space? The space is order of n, right? You will be storing all the numbers. So this is another example, 31342, right? So 3 is the output. And yeah, this could also be one of the examples. So what they are saying is you have to return the repeated element, and that repeated element can come any number of times. So here it is only appearing twice, but here it is appearing like 1, 2, 3, 4, 5. It can also appear like 1, 2, 3 times, and then for the others, you can have 1 to 4. Here You can have, if I pick up 2, then here you can have like 1, uh, 1 or 4 here you can have, right? So like this. So in this case also, you should be having 3 as an answer. Okay, so that is the naive approach. Now we will be looking at the tortoise and the hare, or you can say it as a slow pointer, fast pointer approach, right? From the scratch, we will be seeing this thing. So let's move on to seeing that approach. So these are the two examples that we will see. First thing to realize is that this problem is actually a linked list problem. Okay, I will explain you why and how. If you look at these elements, okay, you can think of these numbers as addresses. Okay, so here, if you see 0, it's pointing out to 3, right? 3, and if you go to the index 3, actually, you are seeing that that 3 index is pointing out to number 4. Then again, 4 is pointing out to number 2. 2 is pointing out to number 3. And there is 1 who is just pointing out to itself, right? So this is a kind of linked list that we are getting. And what is the head of this linked list? Or you can also think of it as a graph. So the head is this. Okay. Why? Why is this the case? So the reason is, if you see what information has been given to us, they have given that the numbers are from 1 to n. Okay, 1 to n. So nobody over here is going to point out to either 0 or less than 0, and nobody is going to point out beyond 4 also, right? So that is the reason we are actually correlating this problem to a linked list problem, right? And what is the head of the linked list? The head is always 0. Why? Because the range is 1 to n and nobody is pointing to 0, correct? So that is the reason why this correlation would work, and we have a head starting at 0. Okay, let's draw the same for the second one also. So here we have 0 pointing to 1, 1 pointing to 3, 3 pointing to 2, 2. So this 2 index is pointing to 4, the 4 index is pointing to 2, right? So 0, 1, 2, 3, 4. We have taken all the elements. And again, the head pointer is over here, right? So think of these numbers. So this is the nums array, right? So think of this nums array as it is storing the pointers, correct? As it is storing the pointers. Why would we think in that direction? Is, if you see what is the output in the first one, the output in the first one is 3. What is the output in the second one? It is 2, right? This is the number which is there. Can you see something in the linked list? This is the output. This is the output, right? Can you make some kind of correlation over here? So if you observe this example, you can see that 1 is appearing only one time, okay, or 2 is all only appearing only one time. So what does that mean? Is that if 2 is appearing only one time, that means in our linked list, only one member is going to point out to this 2, correct? Here 1 is appearing only one time, so only one member is actually pointing to 1. 4 is also appearing only one time, so only one member is pointing to 4. But if you see, 3 is appearing two times. So there are actually two pointers, right? More than two pointers could be there on this particular element, right? So this is the distinction, right? So we can say that whenever we have in a linked list a particular node, and if many number of pointers or more than one number of pointers are actually pointing to this node, that just means that there is a cycle which is starting at this particular node, right? You can see here also, you can see that 1 is only appearing one time. Okay, one is only appearing one time. So that is the reason it only has one incoming edge, right? But 2 is appearing two times. That is why it is appearing twice over here, right? And that is what leads to a cycle, right? That is what leads to a cycle. So somehow, if using this correlation thing, if you're able to find a cycle in this particular graph or in this particular linked list, and if you're able to pinpoint where this cycle starts, that is your answer, correct? That is your answer. So there are two challenges in this. So the first challenge is how do we find a cycle in linked list, right? And the second one is how do we pinpoint the start of that cycle, right? How do we pinpoint the start of that cycle? So let's just go one by one. Okay. So now this is a linked list problem. It is no more uh, array problem for us. So let's just take any linked list. 1, 2, 3, 4, 5, 6. Right. Now, in this particular method or in this linked list, how would we find out the cycle? So again, a naive approach would be to store the elements or the nodes which are there, right? 1, 2, 3, 4, 5, 6, and then when we reach at 6, we see that we are again going to 3, which is already present in our map data structure. So that is the reason. This is how we can find out the cycle. But what if you want to do it in order of one time? So here's where we will use that slow fast method, or it is also called as the tortoise and the hare method, right? We will start our slow pointer and the fast pointer from here. We will increment slow once, increment fast twice, so it will be over here. Increment slow once, fast twice, increment slow once, right? Fast twice, so it just went from here to here. Increment slow once and fast twice, right? So if slow is equal to fast, right? That is where it is the meeting point. Now, in a usual linked list problem like 1, 2, 3, 4, and this thing, right? We don't really know whether a cycle would exist or not. But in this case, so I'm not going to cover that case. But here, if you see, we already know that cycle definitely 100% it will exist, right? So what we will do is we will just keep on doing this thing, right? We will just keep on doing this slow fast thing until and unless slow is equal to f, right? Slow is equal to f, correct? Now, once we do that, okay, so that will be our meeting point of the slow and the fast, right? Now, once we get that point, which is our meeting point, we are going to find out the where we can say the starting point of the loop, right? Starting point of the loop. Now, how do we do that? So the algorithm states that wherever you have stopped, so you just stopped over here, right? You just stopped over here. So wherever you stopped, what you do is just have one pointer. You can use the f pointer only or s pointer, or we can use some other pointer like y, and you can take another pointer at the start of the node and increment once, increment once, increment once, increment once, right? Where these two pointers meet, that will be our starting point, right? Now, why does this work? Why uh, our meeting point, which is there first? So there are a number of questions over here. The very first question is why would s is equal to f will always happen, right? That is the first question that we will try to answer. Like you might argue that you have a loop and you have a slow pointer over here and the fast pointer over here. How can you say that slow and fast pointer will definitely meet sometime, right? It will definitely meet. So that is the first question. And let's say that, so I will be proving this first. And once we prove that S and the fast, let's say they meet over here. Okay, this is the meeting point. How can you say that if I am at this particular position, then whatever this position is, or whatever this distance is, and whatever this distance is. So if I just start from here and I go x in the x distance over here, then from this meeting point, I will also go x distance and I will get my meeting point. So how are you stating this? So I will be proving both of these things. Okay. So, but I think the picture is clear of what we need to do. You can clearly code this up right now and you will be able to do you will be able to get the answer, right? So see, let's just try to answer both of these questions. So the first question is, how can you say that the slow and the fast pointers will definitely meet in a cycle? Okay, so let me take this example. Consider this is the loop and consider your S over here and F over here. Okay, now S is going to go in the forward direction +1 and F is going to go in the forward direction in the +2, right? This is a standard implementation of the problem that our slow goes with +1 every time and our F goes with +2 every time, right? So currently, just note down what is the distance in between them. Let's say that it is X, right? Let's say that it is X. And in the next iteration, my F will be over here, right? And my S will be over here. So you can see the next distance will be X minus 1 in between them, right? So the first distance is X, the next distance is X minus 1. Again, it will be +2. Again, this will be +1. So again, the distance from here to here, which is there, right? That will reduce by 1, which is X minus 2. This is just simple math, nothing else. And so definitely you can observe the pattern that the actual difference in between them is actually just 1. Why can I say that? See, it's like having there are two, there are just, let's say, two kind of trains or something over here. It is moving with 1 kmph and the second one is moving with another 2 kmph, right? So at every kilometer per hour, right, or every hour, what will happen is this one will be going ahead with 1 kilometer, right? With 1 kilometer. So it will be +1, +1, +1, right? But because here we are in a circular manner, so the distance is actually kind of decreasing, right? So we can say that from x to 0, we will definitely reach, right? So it is a simple observation that it is starting with x and then f moves with +2, then it will be x minus 1, distance will be x minus 1, so and so, right? So that is how. So here is where we can say that S and F will definitely intersect, right? S and F will definitely intersect. Now, uh, how long can this X be? This X can be kind of cycle length, right? What is the cycle length? Around that particular length, right? That is the maximum that can go. So that is why we can say that, almost like around cycle length iterations, we will have S and F to be together. Correct? So cycle length is definitely bounded by n, so it is less than n. So what we can say is this whole thing of finding the meeting point, right? Finding the meeting point where S and F both lands, it will take order of n time, and of course order of one space, right? So that is the first question that we have answered. Let's try to answer second question. What is the second question? How can I find the meeting point, right? And here what I'm claiming is if let's say this is the diagram, right? This is the meeting point that I want to find. Let's say that this whole distance which is there, okay, in the red color, it is x, right? Then this distance which I'm highlighting, it is, let's say, y, okay, y, and this distance in yellow, let it be z, okay? So what is the cycle length you can see over here? Cycle length is actually, let us call it as L, which is going to be z plus y. right? Z plus Y. Now, if you see our slow and fast pointer would be over here. Okay, think of them as two people. Two people. Okay, one is slow and one is fast. Correct? Now, if this is the meeting point, M, okay, if this is the meeting point, they have both started around, let's say, 5:30 a.m. and they will both reach at M because of course that is the meeting point where they first meet each other, right? So around 6:30 or something, right? So you can see that to reach a particular meeting point, the time which is taken is exactly the same, right? So can I say that my time which is taken by the slow runner is actually equal to the time which is taken by my fast runner, correct? So that is the first thing, right? This is to meet at M, this is the time which they will be taken, and it is the same time. But what is time? Time is actually distance upon speed, right? So distance of the fast runner upon what is the speed of the fast runner, correct? So let's calculate the distances. Okay. So what is the distance that is actually traveled by this slow runner? If you see in the diagram, it is x, right? As the slow runner will be over here, will be coming over here. Then it will be traveling across the loop, across the whole loop. We don't know how much ever time, right? So let's just call it as, let's say, some constant number of times it will travel the whole loop, right? Some constant number of times it will travel the whole loop. And again, it will reach over here only, right? Because if I am over here, after X, I am over here, right? And again, I will be traveling some K number of times. I will be over here, right? Some constant number of times the whole length I will be reaching till over here only, right? So that is one thing. And once that is happening, so you will like constantly travel the whole loop. After that, I will take y steps to reach this m, correct? So that is the distance that is traveled by the slow pointer. Okay. Let's check at the distance which is traveled by the fast pointer. So what would that be? So again, he also would travel this x, right? Again, he will be traveling the loop, the whole length for some C2 number of time. It will be definitely different. C1 will be definitely different than C2, right? Because the fast runner will actually reach the loop first, right? So he will be maybe traveling for more number of loops, right? Not maybe, he will definitely be traveling more number of loops. And then again, he will be taking y steps to reach that meeting point. Is that correct? Okay. Now, what about speed? If I assume that my speed of the first runner is like 1 meter per second, okay, then what is the speed of my second runner? It is 2 meters per second, right? Because he's twice as fast. Let's just remove this unit so the whole equation will be clear. Okay. Now let's just try to understand this equation. Let's just simplify first of all. So we have 2 into x plus c1l plus y is equal to x plus c2l plus y. Okay, so that would be 2x plus c1, sorry, 2c1l plus 2y, which is x plus c2l plus y. Okay, so the y would actually get cancelled from this side, and here 1, 2 will be cancelled. X and x, right? So finally, what would you get is x plus y, right, is equal to c2l minus 2c1l. Okay, if I simplify this thing further, I would get x is equal to, so I would take this like L out of the brackets. So C2 minus 2C1L minus Y. Okay, so this is the whole constant, right? So let's just replace that whole thing with maybe, let's say, some K times L minus Y. Okay, so this is the equation that we have. Now observe one thing over here. Let me just go back to this diagram. Okay, observe one thing over here. What did we have? We have x is equal to kl minus y, correct? Kl minus y. Now you have to understand what does that mean. Okay, so this left hand side is where I am standing over here. Okay, any person is standing over here. So he is going to take x distance and he will be reaching over here, right? So it is kind of like a timeline. Okay, not timeline of the distance. So he's at a zero distance. So this is a wall. Let's say this is a wall at a zero distance. He will take x steps and he will reach at x. Okay, so that is what this x is. Correct? Just remember how far you are from the wall, right? Now let me also explain this thing, the right hand side. Right, so the right hand side is where you are standing over here at this particular point. So what does that mean is k times l. K times l. What does that mean? See, if you're just moving ahead, you're going far away from the wall. Okay, far away from the wall. But then after traveling the whole L distance, you're again coming back to zero, correct? You're again coming back to zero. So the effective distance that you are actually traveling is zero only, right? What I will do is I will just rewrite the right hand side as k minus 1 L plus the minus y. Okay, so you can see that after some constant number of times, again I am reaching at the same position, which is of literally no use. Okay, it is of literally no use. So the distance that I am gaining from this thing is zero. Distance I am gaining from this thing is zero. This is a very important point to note. Okay. After that, after again I reach, by many number of loops to the same point over here, I will take L minus y distance ahead, right? L minus y distance ahead. But what is L minus y? See from over here, z is equal to L minus y, right? So this is nothing but z. So what did we get? We got x is equal to z. Okay, a very, very important point to note. Okay, so you might ask me a question that why didn't you do this as a zero, right? In this equation only, why didn't you take KL as zero? Because if I did that, I would get a minus y, right? So it is kind of like I am traveling in the opposite direction, right? So in that case, x would be minus y. So again, that would be implying the same thing, which is x plus y. But in order to just make it more understanding, I split this up into k minus 1 into L plus L minus y. So here we are not going to go in the negative direction, but we will rather go in the positive direction, which is the clockwise direction. So this is the clockwise direction, correct? So in that is the reason why I did the splitting, and this is the whole clockwise part, right? So anyways, interpret it anyways. You pause the video and interpret yourself, and you will be landing at this statement, which is x is equal to z. So this is a very important point, right? So your x, which is there, so this z is nothing but x. So if I say that I am at my meeting point over here, right? If I take a pointer over here, let's say it is too messy right now. If I take a pointer over here, maybe you can say j, right? And if I take a pointer over here, I, if I go x direction over here, then I also go in the x direction over here, right? See, if I go in the x direction over here from the starting point and from the meeting point, if I go in the x direction over here, definitely I will definitely land up at the meeting point, right? Because this distance which is there is same as this distance, correct? So that is the fact, or that is the thing that we will use, correct? So what we will do in our code is we will first use the slow and the fast approach. This is too messy. Let me just go over here. So what is the first approach is we will first take our slow and fast over here. Then we will land up at some meeting point where S and F will land, right? So that is our meeting point. Now I have to find out the start of this. I want to find out the start, right? So that is the reason what I will do is I will go to the start element, okay, or the head of the linked list, and I will start another pointer from over here, let's say I and then j, and then I will keep on incrementing I and j one at a time, okay, one at a time. And that's where I will land over here because this distance and this distance is the same, right? So the proof also I have did and I have shown you, right? So now we will go to the coding part of this. I hope that this is understandable. I have not just shown you what to do, but I have also given you the whole proof of why this thing, right? So the very first thing is I think I have shown you why this x minus 1 and sorry, why this meeting point has to exist in an order of n time or almost around the order of n time, right? So why that is true by using the slow and fast approach, why is that true? And the second thing is why would we definitely, how would we actually get to that starting point of the loop, right? Using this approach. Okay, so don't just mug it up, just understand the maths or the logic behind it. So this is the whole maths. Now, now that we understand all of this, it is very, very easy to just code this whole up. Okay, so let's just hop on to the code part now. So this is the code for the approach that we saw right now. So you can see that my slow is starting from 0 and fast is also starting from 0. So this is the index number, okay? Do not confuse it with anything else. So index number as in 0, 1, 2, 3, and so on, right? And we will start with an element which is slow, nums of slow, and nums of. So what this exactly is that slow is equal to slow next, correct, in the linked list. And this is fast is equal to fast next, okay? Because as I said, slow's next is stored where? It is stored in this num slow. So this is exactly what we are doing, right? Where is the fast next stored? It is stored in the nums fast. So this is like we will go from we will go to the first address, and at that address we'll find out the next one. So that is the new address, right? So I don't think that this should be confusing you, right? So what we do is we will keep on doing this until and unless we will get slow is not equal to fast. Correct? Now, at the fast pointer which is there, we will be having the meeting point, right? So I've already shown you what is this logic. The slow is at 0, so I am again taking, I'm not like using two different pointers like I and j, I'm just taking the existing pointer which is slow, I'm just pointing it towards the starting point, and then until and unless my slow and fast are not equal, I will just increment both of them once. Okay, and once they meet, you definitely know that that is the meeting point. So we can just return that particular pointer over here, right? So this all coding logic I have already explained in my logic building previously, right? So the implementation is very simple. So I'm just showing this so that you can see that the code is running and you don't want to code it up maybe yourself. So I will be submitting the code. Right. So it does get submitted. Now let's just move on to some second kind of approach. Okay. So in the original problem, they have mentioned that I think it is here itself. Yeah, you can see without modifying the nums. But if this condition was not given, you you don't really need all of this stuff. Okay, you don't really need the whole first solution itself. I know it is very complicated. So there is a second solution which is much much easier, which I am showing if it is without modifying the array. Okay. So let's maybe take this example itself, 13422. Yeah, so 13422. Okay, this is the nums array. Now, and this is the index. Okay, these are the indexes. Now, use this that I have 1 to n. Okay, all the numbers are going to be 1 to n. So what we can do is we can start from over here. What we can do is we will always see at the first number and try to give or try to put that number to its particular place. For example, let's say if the number at the 0th place is x. Now I will be trying to put it in some x index, right? Like the x index, I will try to put it over here, right? And why would this work? Like, what is the actual logic? The logic is that if at the third index I have already placed a 3 and again I am getting some 3 over here to place, I would check if it is already there. I would check if it is already there. If it is already there, that means this is the duplicate element, right? This is the duplicate element. So let's just try, like I will just try run this for you. So what is our goal? Whichever element is there over here, our goal is to put it into its right element or the right index. Okay. Why am I just considering 0? Why not 1? Why not 2? Why not 3? Why not 4? Because I know that the range is 1 to n. Nobody will be pointing out to the 0th index. That is the reason. Okay. So I would start over here. So I would see 1. Okay, I would see 1. Okay, at the first index, who is there? 3. But I want to put 1 over there, right? So I would just swap these elements. 3, 1, 4, 2, 2. Do not forget the indices 0, 1, 2, 3, 4. So we have put 1 at its right place. Okay. Now again our goal is to put 3 to its right place, right? So at 3 I have 2, so we will just kind of swap these two elements. Fine. So I will just uh, yeah, I will put 3 at its right element, right? So you can see here that 3 is now at its correct position. Okay. Now I will try to put 2 at its correct position. So if I put 2 over here, my 4 will be over here. Correct? So this might get confusing. That is the reason why I'm constantly deleting it. So 4 is over here and 2 is over here. So I have 2 at my correct position. Let's just try to put 4 at its correct position. Okay. So 4 will also go over here. And at this position, I will be having 2. Okay. Now, let's just try to put this also at its correct position. But you can see that already at 2's place, 2 is there, right? So when you try to put any element at its correct position, and if some another element which is matching the index is already there, that means this element that you're trying to put is already existing in your array. So that is why this is the answer. This is the duplicate element. Okay, if you still don't understand, maybe we can take one more example. These things, if you try it out yourself, that will be a lot, you will understand it a lot better. So this is 31342. Let us take this also. 31342. Okay. So 0, 1, 2, 3, 4. Now, what is my goal? To put 3 into its right place, right? So I will take 3 and put it in the 3's index. Okay. And swap the position. Again, 4 over here and 2. So I have put 3 at its right place and 4 at its right place. Okay, now my task is to put 2 at its correct place. So 2 and 2 and 3 will come over here. So I have 2 at its correct position. Now my task is to take and place 3. But if you see at third position, third index, a 3 is already there. So that is the reason my duplicate element is 3. Okay. So this solution is definitely, you can see, order of n. okay? Because there are 1 to n numbers. So every number that we will process over here, it will go either in these directions. And if there is any duplicate element, definitely we will be catching it over here only. And at that time we will return it. Okay. So this will take order of one space and order of n time. Okay. The only thing different over here is we will need to modify the nums array. Okay, but they have strictly mentioned that we should not do this. But anyways, I will just show you the code. So this is the code. So if you see, I'm going to check always the first element which is there. And if at that node, if at that nums node, at that particular index, if I already have this particular number, which is there, that this is the number, right? So if at that index, if I'm already having this number, then I will return that number. So that is my duplicate element. Else I will just swap it up, right? So that is the logic. And if you check, this will also be accepted, right? Yeah. So there it is. So this is how we could solve this problem. It was definitely not an easy problem. That is the reason why it took me a lot of time to just understand and get all the intuition and get all the proofs behind it, right? So I will only upload things when I understand completely myself, right? So that is the reason it took me time. And again, if you don't really understand it, maybe you can just try to go through the proofs more clearly because coding over here is not really a problem, right? Understanding part is actually where you have to spend the time, right? You can see the codes are really small. Even the first submission that we did, it is also very small. Okay, so that's it for this video. Thank you.